Okay. So no one has joined till now. Sorry. So no one has joined till now. So let me wait for a few minutes. Then I'll start. Okay. Let us wait for a few minutes. Then we can start.
Okay. In competitive exams, we should focus the numerical part or theory part more.
Mm, Basically, numerical part. From theory part also they ask, but most of the questions from numerical parts. You have to practice numerical part, numerical question answer a lot. It would be
For
very
jam,
easy. For jam, I'm saying. But they also ask basic question from theory part. They basically ask very easy question. If you know that part, you can do easily. You and that questions don't take much time even. You can just take it like that. But in numerical question, there is one benefit as well because in JAM there is a NAT type question, right? Numerical
yes,
answer type. So for that question, you have to do a numerical calculation only. Um, Probably in NAT question you don't have any negative marking, but uh, I think it's 4 marks question. I forgot actually. Whatever it is, but numerical type of you have to focus on that because if you do calculation right, then obviously your answer will be correct and you will get 4 marks. If the 3 marks, I think 3 marks or 4 marks. So in numerical type question, there is less chance to be get negative. Negative is not there, but I'm saying that if you have done a numerical type of question, then it's more probable to get full marks. I'm saying that. Okay, because you have done that calculation. Yeah? So in between you can do mistake. That's okay. But overall, it's in my case I can say in net. Uh, I did from physical part. I did in 13 question. We have to do 25 4 marks question from all three parts: organic, inorganic, and physical. Out of 60, you have to do 25. So all part has a 20 question, total 60 questions. So I did 13 from physical. From 20, I did 13. And most of the 13 question was numerical type. So that's why among that 13 question, I think 12 was correct. So mm, the chances to be correct in numerical type question is high. So it's better to attend those questions. Okay.
what are the strategy for revision?
Start
Revision in
revision.
physical part. Yes.
And रिवीजन का क्या स्ट्रेटेजी हो सकता है? रिवीजन तो करना पड़ेगा और क्या. Compared to gate and net, jam is very I would say easy exam, because if you have covered whole syllabus na and you have understand those, you can easily crack jam. You don't need to be worried very much. Okay, you have to just stay calm there and you have to attend all the questions. Probably in jam there is no option, right? Option रहता है क्या?
No.
You have to attend all questions. So it's basically uh, that's a different between jam, gate with net. Actually, for cracking net, you need a strategy, you can say, because in net you have to avoid lots of question. You have to select you have to attend only 25 among 60, like that. But in gate or jam there is no as such option. You have to attend all. So the syllabus you cover, as much as syllabus you will cover, that will be beneficial for you. That's the first thing. And obviously try to avoid those complicated organic questions. There are so many steps now in some organic question.
Yes.
Try to avoid those questions. That will take lot of time. And after taking time, the answer you are giving, that might not be correct. 50-50 chance.
Yes.
So if you are completely aware of that question, you have done that question before, you know, you can recognize the question, then you go for it. Otherwise, if the question is totally new to you, probably the mechanism you can predict, but the overall question is new to you, don't do that, I would say. One
I
also
want
two
to
step
focus
is
more on
okay.
the physical part.
Yes, physical part and inorganic part also, because from inorganic part you can get a good amount of marks, because they will ask mainly from coordination part, some organometallic part, some this SPDF, this block elements part, and that question are not much difficult. So you can also focus on those part. Yes, organic part is always difficult. Not difficult, I would say, if you have time on that. But in exam center, that management of time is very crucial. So in that seat, in exam center, doing that organic question may be risky, actually, I would say. Yes. Obviously, for marks will be higher. The probability of getting correct.
Should I make a formula sheet?
Formula C means, okay, just
Numerical
writing down
formula.
all formulas. That you can do. Obviously, you
Yes.
can. That you can do for chapter by chapter. You can also do for this chapter. This is the formula sheet. Uh, Formula, some values, some tricks that you can summarize on a paper for a particular chapter. For all chapter, you can do this thing. You can do. Yes, it will help, because before going to the exam center, you don't need to revise all those chapter 1 or 2 days ago. You can just look at the formulas, because solving numerical type of question, you have to aware of all formulas and you have to keep in mind those formulas. Obviously, that you can do.
Do you have anything related to this?
I had some exam those kind of things, but that is for CSIR needs. Would that be beneficial for you? I have to search it. Where is it now? But I had for all chapters. I had exam rules. If you ask, then
I
I
want
can.
to focus for the physical part.
Okay, I will share, but from that exam rules, you have to select and deselect the part. What part um, is actually included in your syllabus, that you have to check.
Okay.
Okay, because it's based on the net syllabus, no? So it's obviously it will be uh, more in content. So which chapter
Organic and
you?
physical, inorganic also there.
Mhm. All chapter I have. I had, but I have to. search it, or otherwise I have to collect it from my friends. I don't know whether I have it, but I had. But one thing means, which chapter you need that you should mention, then I will search. Okay.
Physical chapters, thermodynamics, and all things kinetics,
Kinetics, thermodynamics,
solid
or
state.
no, quantum will
Yes,
be.
quantum and solid state first.
Okay. Okay, then I will search it.
And spectroscopy also, molecular spectroscopy.
Mhm. Oh, that's something I don't know. I think
Please search it.
Abhi.
No, no. After
Okay,
this class, when
okay,
you have time.
okay. Okay, I'll search. Okay, otherwise I will ask from my friends. They definitely have. Okay, so let us start. Okay. Hmm. Okay, is it visible?
Yes,
Okay. So today we'll discuss first the Gibbs paradox, and after discussing Gibbs paradox, if we have time, probably we have time, then we'll start the grand canonical part little bit, and in the next class we'll complete the grand canonical part. After doing a grand canonical part, we'll focus two class on the numerical questions only. Okay, from the uh, assignments, and I have also some numerical questions. For next after next class, we'll complete the grand canonical ensemble part, and after that we'll do just numerical type of question, and then we'll do the molecular partition function, those things. Okay. So, and what is
the
going on that?
classes are going different.
What is going on that I'm going to ask?
Mayor's theorem
Mayer's theorem.
and cluster expansion things.
Okay, if you say if you have any doubt, you can say me. Then I have to check what is the content for the Nursery class information. And according to that, I will then change. If you prefer, I will do that. I have no problem. Okay, I can do that. But
Okay.
I think probably Baki sir will taught the um, Ising model as well. These things will also be taught. So
Yes,
we have to choose because all things we can't do, right? If we want to do the numerical
yes.
part, then we can't cover it. If we want to do the this part, then we have to avoid the numerical part. Whatever, we will see. First, today we will discuss this part, and then we. Okay.
Okay.
Yes. Okay. So in last class we discussed this, right?
Yes,
Hmm. So today, do you have calculated the entropy?
yes.
Static. Okay. So guide me how to do that. How I can calculate the entropy for monoatomic ideal gas, considering gas molecules are distinguishable. Okay, how we should approach. What is the general formula for entropy?
For canonical ensemble,
Obviously, for canonical ensemble. We know that is entropy was
KB ln Q plus internal energy by T.
okay. In last question, I will do that. So this is our general formula, right?
Yes,
So what is now Q?
total partition function.
Exactly. So this is canonical ensemble partition function. So when you
Yes,
calculate the second-order equation or this kind of equation, should we consider the canonical ensemble or grand canonical ensemble? Here we will consider now first
canonical
canonical.
ensemble.
Yes. Okay. Now first thing, this is our canonical partition function. Means here the distribution, statistical distribution we are considering of the canonical ensemble, not the molecular distribution. Okay. If you remember, we had a infinite number of copy, right?
Yes,
This. This is a infinite number of copies of the macro state, right? And these all copies are called micro
microstate.
state. Yes. But uh, this is not the molecular distribution. When the molecular distribution will arise, when you consider only, let's say, one copy of this, any one copy, this copy you consider, in this copy, this is a copy, means this is a microstate. So among all in case of all microstate, there is a molecular distribution because molecules are moving around. So here you will see the molecular distribution. So when molecular distribution is there, then you will have a molecular partition function as well. This part we will do later. Let's say this molecular partition function is Q, small q. Then this capital Q and how the small q related, this is a very, there is a derivation. I
Q
am
to the
not
power
doing.
n.
Yes, this I am not doing right now. If it is have n number of particles, then obviously, and it is constant for all cases. That's why it's canonical ensemble. If it is a grand canonical, then we can't write q to the power n. It's obvious. So
N is variable there.
n is variable, obviously. So this q to the power n. So this derivation we will do later when we will do the molecular partition function. Then we can do that. Okay.
This also has derivation.
Yes. How can you say that q equal to q to the power n? This
N
that is
number
a
of particles Q into
no no no
multiplied
no
by
no
n
no no.
times.
You can show that. You can show that. It's quite theoretical derivation, but you can get the feelings. Half page derivation is there. Half page derivation is there. I have to check once, otherwise I can do that right now, but I have to check once that it's not ready right now. I I have think that when we will do the molecular particle function, we will start with that derivation. Okay. So it is q to the power n. So if now this q, what is this q? This q is
Molecular partition function.
yes, and this q is actually multiplication of all kind of motion like translational partition function,
Vibrational,
vibrational
rotational,
partition function, rotational partition function,
electronic.
electronic partition function, and nuclear partition function. Okay, all partition functions are there in Q. But when we consider only the monoatomic gas,
The screen has gone.
is it now okay? When it will appear, you can start. I don't know why. Is it
Yes,
okay?
now it's visible.
Okay. So let's say now we are considering the monoatomic gas. So for monoatomic gas, so what is the number of modes?
three translational and two rotational.
Okay, to rotational. How?
Sorry, monoatomic three translational only.
Hmm. Because monoatomic one atom, so n is one. So overall 3n, so 3
Three
should
N.
be the and that is all translational. That's why for monoatomic gas only you can write Q equal to Q translational. Is it clear?
Yes.
And what is the expression for Q translational? We will calculate that later. I'm saying again. We
Two
will
pi
derive that.
mkbt by h square
2 pi
mkbt by h square
h square or h cross? H square,
all to the power
half, right?
half. Yes.
L, L is not there.
What?
L, length.
Yes, length is also there.
So where is it?
Into L.
Because it's an extensive property, extensive partition
Yes.
function. So this is our Q translational. So if it is Q translational, then what will be our capital Q? This should be our capital Q. So just
Yes.
put it. Just check whether this expression is correct or not. Otherwise, everything will be wrong.
Q translational. This is for one translational mode. If three translational mode, then it is whole cube.
We have to consider obviously all three dimensional. So it will be 3 by 2, right?
Yes.
And it will be V
And this is volume.
volume. Yes. So now we can write it as to the power n. So 2 pi mkbt h square 3n by 2 v to the power n. If I am not wrong, this should be correct.
Yes.
Okay. Now, if it is the case, then what is our entropy formula? If you remember Kb ln Q. So first take the first term. So ln Q will be Kb ln Q if you want to calculate. So Kb ln Q will be Kb times 3n by 2 ln 2 pi mkbt divided by h square plus Kb n ln V. Correct? I think I'm correct.
Yes.
So what is now it is what we can write. We have to you can write it like nkb ln nkb we are taking common, so nkb ln g times 2 pi m kbt by h square to the power 3 by 2. Just check whether we can write it or not.
Yes.
Okay, we can write
Three
it.
by two. Yes. Okay, you can write.
This is correct, so it is now 2 pi m h square will not be there now. We have taken h square out. This is KBLNQ.
Yes.
Now what is our E average.
minus del ln q del beta.
Or there is other formulas as well. KBT square,
Yes, minus kbt square. Sorry, positive.
KBT square, then D ln Q dt,
D
right?
L Q dt. Yes,
So ln Q we know. This is our ln Q. Ln Q
just
is this
impulsive
part
derivative.
only without the. So now we have to take the derivative. So just check whether this E average is correct or not. I think it's correct because we have to be very cautious. Otherwise, if you do a mistake later, we can't manage it. Yes, it's correct. It's correct. So what is our ln Q? So ln Q is this all part. 3. So this part will be 0.
Yes,
Only the first part will contribute. So here is T. So 1 by Z. So 1 H square by 2 by M K B T times 2 pi M KB by E square. Just check. Is it correct? Take it as Z. So it is d ln Z by dt. So d ln Z by Z. Oh, sorry, d ln Z by dz.
dz dz dt.
dz dt. So it is 1 by Z times dz dt, and 1 by Z is
Yes, this
this
is
part. This is 1 by Z, and this is
yes,
dz dt. Okay. So 3n by 2t. This is E average 3n by 2t. Then if it is n average and we need E average, sorry, this is E average and we need E average by t. So what will be E average by t? So
3 by 2 nkb.
kb was there, right? kbt square
Yes,
is
kb
there.
is there.
So this that will be kbt, then 3n by 2t square. No, 2t. 3 by 2 nkb. Correct?
Yes,
So what will be s now? What is first term? This whole term. We can again change it.
3 by 2 will be added to this.
No, just recognize what is our E average. E average is this part, right? 3n by 2t.
Yes,
So if I want to replace t from here, so t is our E average is 3n by, no, not E average. E average is 3 by 2 nkb.
yes,
So E average by t, what we obtain? 3 by 2 nkb. Correct? Is
yes,
correct? Hmm. If it is correct, then what we can write from here that kbt is actually 2e by 3n. Check it.
Yes.
Just put it here. Then it will be n kb ln v by h cube 2 pi m kbt की जगह it will be 4 pi m e average. I'm not giving the average, and it is 3n to the power 3 by 2. Correct?
Yes.
So what will be our s finally? N kb ln v by h cube 4 pi m e divided by 3n to the power 3 by 2 plus 3 by 2 n kb. This is our entropy for ideal gas, monoatomic gas, and most importantly distinguishable. This was the formula of entropy. Okay, just check it whether there
Yes.
is any doubt or not. Okay, so what are the constant part here in this formula? Lots of constant are there, right?
3 by 2 nkb.
Hmm. N is not constant.
Yes. 3 by 2 kb.
3 by 2 kb. M is constant. M means
Yes.
if you consider one monoatomic gas, for that particular monoatomic gas, M will not change. 4 pi, h cube, these things all are constant, right?
Yes.
So we can break this equation such that this constant and other part can be differentiated. So let us try whether we can do. It will be 4 pi m by 3, 3 by 2, 1 by h cube. Correct? And we can take this inside. It's also correct.
Yes.
And we can bring this 3 by 2 in front, and we can consider. Okay. So you see here only the constant parts are there here.
Yes.
So we can write it as n kb. These part are extensive part actually. Let us write n kb s0, where s0 is 3 by 2 ln 4m pi by 3 square plus 1. This is a constant, totally constant part. Okay.
In the previous day, we got some constant when integrating the ds value.
Hmm. That
Is
was
this
proportionality
constant same?
constant. That was
No,
proportionality
the
constant.
integration constant.
Oh, integration constant, yes. Huh. No, 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 no. We have already considered that now. When deriving the formula of entropy, this S actually, if you remember, that original S minus this constant,
Yes,
if you remember. So after that, for us, for humankind, the entropy is actually original entropy minus C. That's it. That's just
yes,
a coordinate shift. You can think like that, right?
yes,
Okay, so if this is the case, then let's say if we change n to alpha times n, these are extensive property. We can change the macro state. These are macro state variable, correct? This is alpha times beta and energy. This is alpha times E. Then how the energy will entropy will change, that we'll see. Okay. So new entropy, let's say S prime will be, this will be now alpha n AB ln alpha v E by n, it will be cancel out 3 by 2 plus alpha n kb s0, because s0 is constant anyway, constant, no changes will be there. So it is alpha, it's correct. This is the case. Now what was just see, all the extensive properties are multiplied by alpha. Okay, correct.
yes,
Now what was our previous entropy? S is not multiplied by alpha, you see, because what is our alpha S? Alpha S is our alpha n kb ln.
E into E by N to the power 3 by 2. This alpha is not there.
This is the, so it's not matching.
Yes, the alpha under the ln is not there.
Yes, so that means this is violating the our formula of uh, in extensive property, right? Extensive property means if it is
It
multiplied by
depend
alpha
upon
times, then entropy should also be multiplied by alpha times.
depending on the quantity.
Directly proportional with the quantity, na?
Yes,
If you multiplied all the extensive properties alpha times, then obviously S should be multiplied by alpha times.
yes.
Correct. But that is
This
not
was from the
happening.
classical thermodynamics.
Classical terms, but it is not matching. So something, there is some mistake. This will generate the Gibbs paradox. This factor will generate the Gibbs paradox. That we'll see now. Okay. So it's clear that a formula, there is some mistake. Formula is not correct. So that's why that formula of entropy will lead to us a paradox, which is provided by Gibbs and also solved by Gibbs, and that is called the Gibbs paradox. Okay.
Yes.
Okay. So let us take 1 minute break, then we can again discuss the Gibbs paradox.
Please up the slide.
Okay. Last time probably I did not focus in Gibbs paradox in detail, right? In this
Yes,
much detail. That's why it's important. Just you see, I'm coming to washroom. 1 minute. So let us see what is a paradox. Okay. So just let me write it our formula again. It is audible, right?
Yes.
Oh, it was our formula. So let's take first let case one where we'll consider the mixing of two different ideal gas. Not only ideal, also the monoatomic and distinguishable. This we have already considered. So monoatomic ideal gas is better to write. Example argon and neon, you can think like. Okay. So
Yes. Two non-interacting gas.
hmm, ideal gas, na?
Yes.
These two are the one is helium and one is argon. So before mixing, let's say this is N1, V1 and T1 and it is N2, V2, T2 because we are doing canonical ensemble. Okay. But it was they are kept at equilibrium. So obviously temperature will be same. Canonical ensemble NV. Correct? Temperature should be same. So now I just
Yes.
let the piston up, then it will mix. So when it will mix, then what will be the case? It will number of molecule will be N1 plus N2, volume will be V1 plus V2, and temperature will not change.
Maybe T.
Okay. So now we will just calculate the what is entropy before mixing and what is the entropy after mixing. That is our case. And then we can calculate the entropy of mixing. Okay, we have to just calculate that. Okay, that's our case. So what is our let's us calculate this here S1 for this. What is our entropy? It will be just put the formula N1 KB ln V1. What is the E?
3/2 kVt.
E by N will be same for both cases, right?
Yes. Both is monoatomic.
Both is monoatomic. So N1 N2 are different, but E1 by N1 should be equals to E2 by N2. That, but we can write it here.
Yes.
Let's see. S0 will always be S0. Correct? This is before mixing. And
Yes.
what is after mixing?
Number of particles is N1 plus N2. Volume is V1 plus V2.
This will be
E1 plus E2 by N1 plus N2. N1 plus N2 kbs0.
okay. So what is our del S? Mixing. This is, we can break this part ln. Let's say this is V and N1 plus N2 is N. Okay. For sake of our convenience, we can consider this is N, this is V. For our
Yes.
calculation, it will not be problematic, I guess. So it is ln kb. Actually, let's say it's E by N minus N1 kb ln V1 plus N1 kb ln E1 by N1 to the power 3 by 2 plus N1 is 0 plus N2 kb ln V2 plus N2 kb ln E2 by N2 by 2 plus 2 kb S0. Correct?
Yes.
This part easily cancels because N1 plus N2 equal to N. Nothing is there. So it is just N kb ln V minus N1 kb ln V1 plus N2 kb ln V2. This is one part, and another part is there, that is, okay, what we have argued that E1 by N1 must be equals to E2 by N2 must be equals to E by N. Correct?
Yes.
So if it is correct, then obviously this part will also be cancelled.
Yes. The total E by N will cancel.
So finally, we left with N will be N1 plus N2. So just take N1 common here. So it will be N1 plus V means V1 plus V2 by V1 plus N2 kb ln V1 plus V2 by V2. Okay,
Yes.
it is greater than 0 always.
Yes.
Just we can take an example. Let's say we can take example. Let's say N1 equals to N2 equals to some N, and if it is V1 equals to V2 equals to some, let's say, V, then what will be our result? Then del S will be, just we are considering both N1 and N2
N
and V1
kb
and
will be
V2.
common.
So N kb ln 2, right?
2. Yes.
Plus N kb ln 2.
N kb ln 2.
So
2
it
N
is
kb ln 2.
2 N kb ln 2. And it is always the greater equal to 0, you can see. So this is our, that is no problem. Okay.
But this del S should be 0.
This is different gas. For different gas you are mixing,
Okay.
so
For different
obviously
gases, it will be different.
randomness will should be increased, right?
Yes.
From classical mechanics, you also know this. There is
I
no
say
problem
because
eventually.
we considered N and V are both same.
That's okay, but gas are different. Gas are
Okay.
different.
Gas are helium and argon.
Constantly on argon.
If I consider same gas, then also this result will be same.
Repeat it.
If I consider same gas, then also the result will be same because here is
That
not the
will
parameter.
that will now check. Now the mixing of the same gas we'll discuss. As long as everything is fine, no confusion is there, right?
Yes.
Mixing of same ideal gases. Then we will see what will be the changes. Okay, correct?
Yes.
So you see, in this derivation, do you have considered anywhere the different gas, these features? The gas are same or different? Anything was there for if the gas are let's say same, then also we have to repeat the same calculation. Nothing will be changed.
Yes. I
So
was
for
feeling that.
yes, so for same ideal gases also you will have the same result because nothing is there. This is a general derivation we did, right?
Yes. No parameter for this different thing.
Nothing will change. There is no essence of that different gases mixing or same gases mixing. There is not as such any essence. So eventually that will be. But you know, or you should not know. You can think if these two gas are the same gas, let's say same gas, then why should be any entropy increment? Correct.
Yes.
Previously also the gas will enjoying the same volume V1 plus V2. Now also V1 plus V2. Number of molecules are also same. N1 plus N2. Temperature is also same. Gas are not interacting gas. Then entropy should not be changed, right?
Yes.
So, but that is the paradox. That is the paradox. But according to this formula, you can see the entropy is positive, mixing entropy. So here del S should be zero because it's the same gas. Same gas. Let's say helium, helium. It's also helium. Why there will be any problem? Oh, yes, I will agree. It will be positive or negative something if the gas are interacting. Gas are not interacting. So why should be there
Yes.
any entropy of mixing? No mixing. That is the paradox. So where is the problem? That is our challenge. Now it's clear what is the Gibbs paradox now. This is the Gibbs paradox.
Yes.
Mixing of same ideal gas. So how you can resolve it? Any idea?
By the distinguishability parameter.
Exactly. Otherwise, everything is okay. We have considered the gas molecules are distinguishable. That is not. Why the gas molecule will be distinguishable? How you can distinguish the gas molecule?
Yes.
So gas molecules are not distinguishable. So
All are
we have
same.
yes, we have to consider indistinguishability of gas molecules. We have to consider. Okay, that is the catch. So if that is the catch, so where it will be changed that now Q will be not Q to the power n, but Q to the power
By
n
n
by n
factorial.
factorial. Okay. So
Yes.
now you can do the calculation again from here. Just everything will be same. Just you have to consider this will be one more term will be there. That will be Q factorial. Just I will copy paste. Nothing I will do. I will just copy paste from here and we will see what will be the change. Okay. So what will be now
Yes.
changes? It will be n factorial,
By n factorial.
n factorial. Here we also will have a n factorial term. So if there is n factorial term, so you have to minus kb ln
Ln n factorial.
n factorial. So here will be kb ln n factorial. Here also the same case, ln n factorial, but it will not affect because after derivative it will be 0. Correct?
Yes.
So only changes will be there. Here it will be now minus kb ln n
N
factorial.
factorial.
So how you can do it? N factorial is ln n
N ln
factorial
n
is,
minus n. N ln n minus n.
yes, that is our Starling
Starling
approximation, right?
approximation.
So it will be kb n ln n minus n. Correct? So what is
Yes.
our second? So now if you do it, so it will be n kb ln. This ln will be included there. Correct. So we can write it as, how we can write it? 1 kbn will be there, so it will be 5 by 2 n kb, right?
Yes.
It's sure. And here 1 n will be included, ln n is there, so you can write it as just,
Yes. This term.
so this should be our now equation for entropy. This is considering indistinguishability. This is called our famous Secured equation, right?
Security. So what was the previous equation?
That is not named actually. That was the failed attempt. That you can say Secured equation for distinguishable molecule, kind of that. So this is a Secured equation. So now we can again reorganize this equation. How? Just take n kb ln, t by n is there, e by n to the power 3 by 2 is there, then it will be n kb ln 4 pi m by 3h square to the power 3 by 2. 3 by 2 will take outside, and it will be now, okay, 3 by 2 take, okay, it will be now 5 by 2 nkb. Okay, now you cannot take common. This is, so you can write it as n kb ln again n kb s0. So what is now s0? S0 will be changing now. S0 is 3 by 2 ln 4
4 pi
pi
m by
m
2
by
square.
3h square plus 5 by 2.
Yes.
Now we will do the same calculation. We had done the mixing calculation for different gas and for same gas. Okay,
Yes.
so let us check case 1 for different gas. So before mixing it was, what is S1? Just n kb
N1.
n1 kb ln v1 by n1 e1 by n1 3 by 2. Correct? And after mixing,
S1, N1 plus N2 direct considered N.
Uh-huh. Okay. So what is del S? You see this part will cancel, En
S1,
part
2.
will also cancel.
Yes.
But here you see, you have to just now consider V1. Then there is also N. So it is now not like that. It is like this. This, correct? Or if I'm wrong, I think it's correct.
This is in terms of N1.
If you break it, N1 plus N2, then you will have this term, right?
Okay, yes.
No? Just let me check all the. This we will get, I think. V is V1 plus V2. And if you take N1 common here from KB, it is V1 by V2 by V1. Oh, it's okay. And one more term will be there. That is N2 KBln V by N. So V is again V1 by V2 by N1 plus N2 times N.
Yes.
This will be our answer. So now it is positive or negative.
It should be greater than equal to 0.
Greater than equal to 0, but from these equations you can say this in part why they are not right in 1 minute. Let me check. Oh, sorry. We had done a mistake. Sorry. We should not be
What mistake?
right. Uh-huh. We have done mistake while doing step jump. Just copy. Let me copy paste the figure. This is different gas, right?
Yes.
So what will be now S12? S12 will be
N1 plus N2.
no. Here the gas molecules are different, right? Gas molecules are different. So we have to consider differently, separately. Means here we can say it is like that. Before previously also we had done same. Here also we have just added it, but we have done same. Actually, S12 is eventually S1 plus S2 after mixing also.
Then delta S will be definitely 0.
No, just do it S1 plus S2 after mixing
Delta
S1
S
plus
is
S2.
S1 2 minus S1 minus S2.
No. This S1 and this S2 is actually before mixing S1 S2. After mixing, like, it will not. It should not be written as S1 plus S2. But I'm saying actually it is before mixing. Let's say 0. After mixing, this will be the case.
Okay.
What will be S1 and what will be S2? Jaga nahi hai, Rani. Let me do it. Just do S1 will be after mixing. What will be S1? This is before mixing, right? This is before mixing.
Yes.
After mixing, it will be N1, KB, Ln. This will not be now V1 because it is enjoying the total volume. So it will be
Yes.
V.
Total volume V.
The energy will be total energy.
E
Your system is now total energy E. What will be now? What will be the number of particles
N
in? Because you are now considering the sorry, this will be now total number of particles. Yes, no, it is S1. So it is N1, not N. And then it will be 3 by 2 plus N1 KB S0. This is S1, correct?
yes.
What will be S2?
N2
N2
KB ln
KB
V
ln V E
E
by
by N2.
N2 to the power 3 by 2 plus N2 KB S0. Just add it. You are having the same thing or not? Just check it.
Can I do N1 plus N2 is N?
Hmm? Okay,
I am getting the same.
same na?
Yes, as the previous one.
Previous S1, this one. No, there it is U1 and it is V1. It is different.
Yes.
Okay, let me do it here. It will be understandable. So let's say it's before mixing, so I'm putting 0. So it is after mixing. What will be the case? It will be N1 KB ln
V
V1 by N1. Then what will be the energy? Okay, this V should not be V. This should be V. Total volume. It is enjoying
after
total
mixing.
volume. It is enjoying the total volume, right?
Yes.
3 by 2. Then N1 KBS 0 plus N2 KB ln V by N2 E2 by N2 N2 KBS 0. Correct?
Yes.
So what we can write? N1 KB ln V by N1 plus N2 plus N KBS 0 plus N1 KB ln U1 by N1 to the power 3 by 2 by 3 by 2. Okay. Is it okay?
Yes.
So now just take the del S. The one, this part n kbs0, this will cancel definitely, and this n1 kb1 by this part will also cancel. So only the survived part will be n1 kb ln v by n1 plus sorry n2 kb ln v by n2 minus n1. What you can write
V1 plus V2 by V1. Yes.
the same formula you
Ln
are getting.
V1 plus V2 by V2.
So just let me correct it here. It is actually you. Now it's okay. Okay. If you do it, then just considering this, you have to do this calculation. And you know this E1 by N1, E2 by N2 are same, so you can do it. No problem is there eventually.
Yes.
Okay. So there is no problem. But it's better to do separately. Okay. So it is our mixing. It's correct for different gas. And it is obviously greater equals to 0 as we have expected. Mixing of same gas. So in case of mixing of same gas, what will be the changes? This will be same, right? S1 and S2, 0 part is the same. There is no changes.
Yes.
But after mixing, what will be the values that we have to check? These are the before mixing. These are the before mixing. But after mixing, what is our S1, 2? That we have to. What is S1 now? Just let me draw it. Same gas. Correct? So what is now
Yes.
after mixing? What is S1? What is the number of molecule?
N.
N. Same
No, sorry.
gas.
N1.
It
N1.
is now same gas. It is total same gas, right? It's not different gas. So how you can write
Yes.
it N1 and N2? It's the same gas. It's just N.
Yes. N.
Kb, Ln, volume is V by N, total energy E by N to the power 3 by 2 plus N Kb plus 0. As simple as that.
But the gas was what was in the first chamber. That was not the number of particle N. That was half
Hmm?
of N.
I don't understand. Repeat it.
Sorry. This is entropy after mixing.
After mixing.
Total total entropy of the system.
Hmm.
Okay. Then it's okay.
You can't differentiate now which you first gas, second gas. How you can differentiate now?
I thought this part was for S1.
Oh no no no. This is before mixing. This part is before mixing, and this is after mixing.
After mixing, total entropy is this S1
Hmm.
2.
S1 plus S2.
Okay. Then NVT.
Correct.
Yes.
So what is del S?
S12 minus S1 plus S2.
This part will be 0 because you know E by N equals to E1 by N1 equals to 2 by A2
Yes,
NP. That part I'm not writing, and this part is also 0. That's N1 KB ln. Just you see in previous case, this by N was not there.
yes,
So you can write it now N KB ln V1 by V2 divided by N1 by N2 times N1 by V1. Now we have to simplify this. How we can do? Then write again we can write just like the same thing we have defined. If you remember, these are not extensive property, right?
yes,
That's why it's the same. Similarly for volume as well. Correct?
yes,
This should be same. So what will be this? N1 KB ln 1.
yes.
Okay? Is correct?
If I put all N1 V1 is equal to NV, and then it will be 0 also.
All
N1 equal to N2 equal to N, and V1 equal to V2 equal to V.
whatever it is. Does not matter. This is always valid, right?
Yes, it is 0.
And you know, if this is true, then automatically this is true. Mathematically, it's true.
Yes, mathematically.
And physically, it's also evident that it will be. So now the entropy of mixing is same for same kind of ideal gases. Okay. So now Gibbs paradox is resolved. Okay. Now we can go to the grand canonical part. But just revise it. If you have any doubt, you can ask. Okay. I'm giving you 2-3 minutes, then you can start.
Okay, I am just checking the whole derivation.
Just take it. Is it okay?
Please wait, I'm checking.
Okay, take your time. We'll start at 5:30.
This secretary equation is valid for canonical ensemble only.
What do you think? Microcanonical, that is nothing, right? It's only canonical.
Yes. For grand canonical, there is another formula.
That will be more difficult. But I have told you one thing, if you remember, after some time, you can see, you can show that all the ensembles will be merged to a same thing, right? Canonical, grand canonical,
Yes.
microcanonical, all are the equivalent. So then you can use this formula as well.
This is unbelievable thing.
No, 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 no. You will see. Statistically, it is correct.
I have checked all these things.
Okay, there is no problem, right?
Yes, I'm getting the same thing.
Okay. So now we can start the grand canonical one. Okay. चलो, grand canonical participation. Okay. So just copy, let me copy paste that box again. For grand canonical, remember this will be
Mu VT.
VT.
N is
That will,
allowed to change.
yes. So it is an open system. So these walls are basically,
Penetrable.
so it's not rigid even. For canonical ensemble, walls were rigid,
Not
correct?
penetrable.
Yeah. But here walls are rigid because volume is not changing eventually, but particle can flow. Okay.
Yes.
So let me start. If you remember the derivation of classic canonical ensemble, just we'll do same thing step by step. We'll do the same thing. Nothing, no changes are there. Everything will be same. So in canonical ensemble, there are These are the microstates. So we have said that there are some eigenvalues of microstate, and these eigenvalues are energy values, because energies are not same, energies are different. Correct?
Yes.
So here let's say E1, E2, E3, E5, E4, again E1, E2, like that. Now N is also now variable, N1, N2, N4, N3, something. So N is also not the same right now. Correct.
Yes.
So previously these eigenstates, in case of canonical ensemble, these eigenstates were defined by the energy value E1, E2, E3, E4, E5, and so on. And we said that let's say in case in E1 there are E1 number of microstates with energy E1, A2 number of microstates with energy E2, A3, A4, A5, and so on. And we said ultimately that okay, that's correct, but overall energy levels Aj sum
Capital.
over J, that is the number of copies that tends to infinity, that's capital A, and overall energy should be same. Overall energy should be constant because the overall temperature is same.
Aj is equal to
So
E.
this we have considered. So but
Yes.
here you have to remember the state. Let's say the energy say E1, probably there are, let's say, two states are there, two not state, two microstates are there, both has energy E1, E1. Then previously in canonical ensemble both were counted in the same state. Correct?
Yes.
But here particle number may be different, so particle number can be changed. So now these states are not the same state. In case of canonical ensemble, these two states were the same state. Correct? A1 will be 2 if it was canonical ensemble, but it is a grand canonical ensemble now, so we can't say these two are the same state. Both are the different state. This state we will have to say E1 in one state and E2 E1 in two state. Correct? Is it clear?
Yes.
So now we have to label the state with two variable E1 N1, let's say, then E1 N2, E1 N3. For E1 is going, again in between there might be E2 N1, E2 N2, and that will also go. So you can see there are huge number of levels. Means just like among E1, it will be now these amount of levels are now out. So, previously all was E1, but it is now E1 N1, E1 N2, E1 N3, and so on. Do you get it? Just like in electronic level, there are vibrational level, and vibrational level, there are rotational level. These things you have seen, right?
Yes.
Kind of that. This splitting occurs. So now we have to
Please
specify.
explain it once more.
Okay. So previously all states, because N was same, right? So all was E1. All of the microstates having energy E1 will be considered in this state. Correct?
Yes.
In this state. But now let's say those energy state microstate we are taking whose energies are E1, all has energy E1. But now it is sure that these are not the same state because the particle number are different now, maybe different. Let's say it is N1, some has N2, N3, N5, something like that. So here this state will be now splitted.
Okay, so there is more than one E1 level.
E1 is same, but N1 are different. So energy levels will not be
Yes.
same right
So
now.
yes. So for E1 energy value, there will be different levels.
Different levels. So now it will be against E2 will be against splitted, E3 will be against splitted, E4 will be against splitted, E5 will be against splitted in this way. Okay, get it?
Yes.
So we have to use some notation. But one thing now what will be the occupation number? Occupation number will denote, previously it was AJ, correct? But you see
Yes.
it is now AJK because the J is for energy N is for K is for
K is
particle.
for
Now
N.
a state will be defined now Ej Nk. Previously one eigenstate was defined by just only Ej. Correct?
Yes.
Now the eigenstate will be defined by Ej Nk. That is our notation. And the occupancy of that eigenstate is Ajk. Clear?
This is for the whole E1.
No, 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 not for whole, all state, all state.
All state where energy is E1.
Not energy C1, it's general. Any general state, how you can denote? What should be the
Okay,
term
then
in that?
AJ. AJ,
For this, it will be A1K. Now K will vary.
please give one example.
This is not this for this energy state. It is A1K, right? This is A11, A12 occupancies. How many microstates are there?
Okay,
This means A1K means there are A1K number of microstate with having energy E1 and particle number Nk. Or A11 means energy state E1 and particle number N1. A12 means energy state E1, particle number N2 means this state. This state.
okay,
A1, this one, right? So just
yes,
if you just sum over A, J, K with just K, then you will have the all total population with the energy level E1. Just see
yes.
A11, 12, 13, and so on. If you add, then it will be just A1. So it is AJ. This is the population with the energy level E1, considering all the N. Clear?
What is the definition of capital A?
Just coming. Now again, if you again sum over J, AJ, then you will have the total number of states.
Capital A.
Capital A. So capital A is actually sum over J, sum over K. That's it. Clear?
Yes.
Now, what will be the total number of energy? It's easy. We have no. This is
Sum over
our
AJK EJ.
EJ, and this
Yes.
AJ is AJK.
Sum over AJK.
Correct?
Yes.
Or it should be written as like this. We should be correct actually. Because the energy state is now EJ. Energy state are EJNK. Energy states are now
Yes.
EJNK.
EJNK.
But we can write it. It's not wrong. It's correct. It's correct. This total energy. And
For the energy state, what is the K?
correct. What will be total U? This is just A1 times E1 if you want to. What will be the first term? A1 times E1. And what is A1? This is sum over A, K, all the K. All has the same energy, na E1. Just that's why it's multiplied.
Yes, all the same.
Same energy. That's why. Correct? And what is our total number of particle? That will be easy also. What will be our total number of particle? Let this A, J, K is a state. This is the number of microstate present. Okay. And in this, how many number of particles are there? NK.
Yes.
Just you have to sum over K. That's it. Sum over K. And after getting sum over K, it is just sum over N. Just see. That should be, because j is there now. So we have to take the sum
Yes,
of j as well. Okay. So it is our total number of particles. There's one more sum is there. Nothing is changed. So now again the same thing we will do. How we will do? Um, we have chosen. You remember combination. Particular set oriented just like AJ, A1, A2, and we have calculated the probability of having that orientation. Correct?
yes,
That we have calculated. Here also we'll calculate the same. Just so what will be our omega? This is our omega. This is the means the number of microstate with this orientation. Now it is JK. Same thing. So it will be a factorial divided by, now two variable will be there. AJ. Previously it was just AJ factorial. If it is confusing, just go to the canonical ensemble part and you check it, you will understand. Just digest
yes. The
this
K
part
term is
only.
new there.
Just digest it, then we'll proceed.
Yes, just the K part is added here.
Hmm. In previous case, if you remember, we have done the same thing, but just our set, that set was just AJ. But now the
Yes,
energy levels are not J. Energy levels are JK. Eigenstates are denoted by JK. So all energy you are choosing a particular pattern, right? Orientation. So we have to choose all energy states. That's it. So we have to consider both. Or you can do step by step as well. No problem. Is the first you can do AJ, then AJ. These you know. Just let me do. This is nothing is there. AJ factorial, and AJ is what? Sum over AKJ. That's it. Okay. Is it okay?
yes,
Now these energy levels are denoted by, I have said, AJK. So considering two variable always, it's quite problematic. So we will just denote as A, some other variable, let's say N. Instead of JK, we are using M for sake of our convenience. But if you remember, there will be other probable distribution as well. This is one AJK. You will have another distribution. You can have, correct, if you remember.
yes,
So we have to consider all distribution, and then we have to calculate the average. After that, we will see that okay, there may be many other distribution possible, but there will be a most probable distribution, and that will dictate, correct?
yes.
And so we will only consider the
Most probable distribution.
most probable distribution. See, other distribution doing that same calculation rigorously, we don't need it actually. We know that ultimately only the most probable distribution will survive, so we'll just take that. So it is the most probable distribution, and you know how you have to find out the most probable distribution.
Yes,
That we will do. We have to maximize, right?
Derivative, it, yes,
Yes. So ln factorial. So it will be kj ln akj. Correct?
yes,
Star I am not giving. After maximizing, what will obtain? That will be the most probable one. So we have to differentiate with respect to akj. Okay, correct? So, but if you have, we have to keep in mind, we have to consider the restriction as well, Lagrangian multiplier. We have to remind that. So
yes.
we should not derive derivative with only ln omega minus, if you remember, these things is there, beta, these things was also there, and another thing, let's say gamma, three restrictions are there right now. Previously it was two,
Two restriction.
now it is three. So these three, after doing derivative with respect to akj, it, this is our task. This we have to do.
This is very complex things.
No, 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 not complex things. First part we have done already.
Yes, first part it's okay.
कुछ नहीं होगा, चलो करते क्या है. Del kj, it is ln omega. Ln omega is a ln a. This will be 0. I'm not doing, just I'm writing. So you can write it as akj. Correct?
Yes,
So what will be that? Derivative. First akj will be stand, then 1 by akj, and then akj. And one minus sign is there. Okay? So it is
yes.
minus, okay, okay.
Minus 1.
No, if you remember, one thing we missed, this k prime, j prime.
Yes,
Differentiate, we had
K-Benji.
to differentiate, right?
Yes.
That is there. So it is ekj, but there is delta k prime, delta
Honecker delta
j
K,
prime.
K, J,
These
J,
things also be there. And for the
cross
second term
terms.
as well. So from second term as well. So it is ln kj, it's correct. But for all, there will be a this.
Honecker
So
delta K, K prime, J, J prime.
exactly. So it is now minus sign there, minus ln a k prime, j prime plus 1. Correct?
Yes.
Great. Second term. What will be the second term? Alpha is constant, nothing is there. So it is just alpha del a k prime, j prime. Then sum over k, sum over j, a k j. So it is alpha. Then it will be just sum over k, sum over j 1, but delta k prime, delta j prime. So it is just alpha. Same thing.
Yes.
Correct? like a canonical, if you done, then everything will be straightforward. Not because these
Yes.
things already we have. Similarly here also beta 2aj. So now these things. Now how we can handle this? Same thing. Akj will be ej is not akj will be derivative, so it will be just ej, but delta jj prime, delta kk prime. So it will be solved by beta ej prime.
Beta ij prime.
And lastly, gamma, what will be a kj nk. Similarly, gamma
Gamma
kj,
nk prime.
correct. So ultimately we got minus ln a k prime j prime minus 1. Then these things are all minus, so minus alpha minus beta ej prime minus gamma nk prime equals to 0. Correct? So ln k prime j prime, that will be minus alpha prime minus beta ej prime minus gamma nk prime. Okay?
Yes.
Same treatment we are doing, if you see. So what you can write? A k prime j prime equals to e to the power,
Minus alpha to the power minus beta ij prime
just
to
see
the power
one
minus
more
gamma
extra
nk.
term is there. In canonical, up to this we
Yes.
had obtained. This is the extra term we
Same as
got
the
here.
previous.
Same as the previous. Okay. So now what we can do now, we can put a summation both side, kj summation. This we have already done. Okay, but we can do it later. Now, after doing summation, what will obtain? This will be a. Just see what we can write. Can we write it? Putting summation
Yes.
both sides. So what is this part? This power minus alpha prime part.
A by sum over j to the power minus beta ij into
Correct.
sum over k to the power minus gamma n.
So what is our now a k prime j prime? We have to just replace this here. So e to the power minus beta ej prime e to the power minus gamma n k prime. This prime is not in j. You have to keep in mind that.
Yes.
And this summation on j prime k prime. Sorry. Correct?
Yes.
Now we know these are the dummy variable k, j, k prime, j prime, so we can replace it. And these are the sum, so we can take it same side. This is ak, but one thing, a is there, so a it is there. Okay,
Yes.
so what is our tjk then, or kj? That is, we know that is akj divided by a, so it
Sum.
is,
Yes. Whole term.
you see the same calculation, only one more extra term is there.
Yes.
this, and this is called our grand canonical partition function,
That can provide an function.
and this is denoted by it's a this function of gamma, beta, and volume. Volume is
Temperature.
fixed. No, volume is fixed. This E, J, N, K, all are the function of V.
Yes,
Just
gamma,
like
beta,
in
and volume.
canonical, it was NV. Here it is V. N part is now there, so it only V left. Correct? So it is sum over J, sum over K, e to the power minus beta Ej, e to the power minus gamma Ek. Okay, this is our grand
Yes.
canonical partition function, or better to write it like this. N is not the number, is function of volume, yes, also. So, like that. But this is not, V is the same. Okay. So this is our grand canonical partition function, and what is our P probability? Sorry, Kj or Jk, whatever it is, same thing. So it is also same gamma representing V. It is e to the power minus beta Ej, e to the power minus gamma Ek divided by
Total grand canonical partition function.
yes. Okay, so this is our. Now if you want to calculate any average, x average, then you know how you can calculate it. Like that way, same thing. So it will
Yes.
be divided by this. This will be our average. Okay, in this way you can calculate. Same thing, just one extra term added, nothing is there, and the energy now the levels are kj. Okay, just
Yes.
go through it, and if you have any doubt, you can ask. In next class, we will calculate the various properties from grand canonical ensemble, and then it will be completed. Just go through the derivation and just compare it with the canonical ensemble. I think it is easy. If you have done canonical ensemble, there's nothing is most difficult part was that most probable distribution, that part. That we have
Yes,
not
that was
discussed.
also easy.
But in canonical ensemble, if you remember, that was confusing. You face some
Yes.
trouble to understand that part. But now we know that most probable distribution will only contribute.
I will revise these things.
Sure, do it by your hand, because you see, if you know
Yes.
canonical, grand canonical is very easy. Just you have to aware of these notations. You can't mix it. Notation wise, you have to be correct, then it will be okay. Obviously, next class we'll calculate the internal energy. But here one thing is there. Now the number of particle is not constant, so n average will also be there, or average n.
Yes.
That we have to also calculate. And as we have seen that this beta is actually, we have proved first that this is 1 by kT, and later we show that this k is actually kb by equating with the gas equation. Correct?
Yes.
So this is actually 1 by kBt, but this we will show here, it is actually mu by kBt.
Mu by kBt.
That we will also show. First it will be mu by kb, mu will be as just a constant, then we will see it is actually the chemical potential. That's the case. for proving that that is KB, we needed that gas equation. Here also we'll considering that our to recognize this constant as mu chemical potential. First we will consider as a arbitrary constant. Then we'll see actually this is mu when we'll consider the dilute solution that dibivocal. From dibivocal we can recognize this is actually a mu. We have to consider some practical example, na? Then only we can find it out.
Can you prove it is equal to del G by del N?
No, in dibivocal, if you relate, if you put in dibivocal mu is G by N already. That you
Yes,
don't need to prove right now. That you know from classical thermodynamics what is mu. That you know in dibivocal mu T KBL and something what was the formula I can't remember. Uh, mu is KBT LN activity something right now.
yes.
So that we can show that that mu is actually this mu. So then we can say okay, so this is the chemical potential, nothing else. This part we will do. Then this total ensemble partition function, this part will be completed. Okay. So let me stop the screen sharing first. Okay, just go through it, go through this part, this canonical part, and this then do it this grand canonical part as well. Then probably it will be very clear to you. Okay. So in next class we will
Okay.
do rest of the part and then send me the assignment questions. I'll solve that, and I will also go through the lectures because you are saying different things are teaching in class. So I will also look at if
I
I
am unable to understand those things.
okay. I think that is not very necessary things as well for you even. If you want, then we can also discuss
The
that.
Mayer's expansion, that's
That's quite different thing actually. Okay, that is quite okay. I'll see. I have to study a bit about that. I know a little bit, but next
in
class we'll
which book
complete
this is
this grand
written?
canonical. This Mayer's theorem.
Yes.
That I don't know. That I don't know. I have to check. Okay, let me first complete this grand canonical, then we'll discuss this Mayer's theorem. Okay.
Okay. Thank you.
Okay. Okay. Thank you for joining today. And again, we will meet next class. Next class, we will complete this grand canonical and the assignment, few assignment question. After that, we will do that Myers theorem and the Ising model, whatever you will teach. I have to see what is teaching going on in the class. Okay.
Okay.
Okay. Thank you for joining. We'll meet again next week.